All right, folks. Well, let's get into looking at a little bit of computation in C++. So now we want to be able to actually get information from the user, do some computation with it, and display the results in some kind of reasonable fashion. So I think this is more or less where I want to go today. Essentially, to get there, we have to look at how and where we can store data. So some of our different storage options, what kind of data we can store, and for today we'll limit it to integer values, real numbers, and individual characters. We'll look at what kind of limitations there are on the kinds of data we can store, so how big an integer essentially, or how big a real number, or what kinds of characters can we store in these things. We'll look at a special symbol or operator used to assign values to these storage locations. So to say, okay, I want to put this value in this location. And we'll take a look at the implications of actually entering specific values directly into our source code, directly into our C++ code. So we'll see some of the drawbacks associated with that. And again, we want to go through the basic math operations, the basic computation process, and just see where we get to here. All right, so any data that our program works with has to be stored someplace, right? It's got to be in there somewhere. And generally speaking, we don't want a program that just does the exact same thing on the exact same value every time. So usually what happens is at some point in the program, it gets information from the user and processes that information and displays some results. So generally the value we're going to be processing isn't known until the program starts running and actually asks the user for the information. So since this data is determined sometime during the run of the program, and since it varies over time, changes over time as we stick values in and change values, we refer to these things as variables, right? Again, their content can vary over time. So these are going to be our most common storage location. So to create one of these things, we have to tell the compiler, we actually have to write C++ code to say, okay, I'm going to use a variable, I'm going to give it a name so I can refer to it throughout the program, and I'm going to specify what kind of information that particular variable can hold. Is it a variable to hold integers, or to hold real numbers, or to hold characters? So for each variable, we specify its data type, the name we're going to use for the variable, and proceed from there. So the data types that we're going to start off with are called int, float, and char for integers, floating point numbers, real numbers, and characters. So int, all lowercase, is the data type name for integer variables. So to create an integer variable, or to create a variable, you give the data type, so let's say int, whatever you want to call that variable, and we usually try and give it a name that's kind of descriptive of what we're using that variable for. So age, for instance, and then a semicolon, right? This is going to be a C++ statement, so it's going to end in a semicolon. So int, age, space is important in there, and the semicolon. Right? So this tells the compiler to go and create one of these storage locations. If we wanted to create another one that was going to hold temperatures, and we decided we were going to use a real number for that, so a floating point number, the data type is called float. So again, it would be float, temperature, and a semicolon. Right? So if we were going to take a look in an actual main routine for something like this, let's actually just pop over and create one. So I guess I should SSH in. Try and remember my password. All right, so let's cd into csci.viu.ca and we'll do some work there. So let's create something for experiments. And let's cd into there. Okay, let's try creating a little program here. And again, I'm going to use Vim for my editor. Oh, I should use Pico since that's what we're going to be playing with for a little while here. So let's say Pico variables. .cpp. So we're just going to create a little program that's got a couple of examples in it, and we'll just play with this over the course of this this session. So we'll do our hash include csd.viu so we can print stuff out. Our int main, and we'll create a couple of variables. So let's create, again, let's say an age variable. And I'm going to throw a little comment in here. So again, this uses the 2 slashes and a variable to store someone's age in years. And a float temperature. Again, variable to store current temp in degrees Celsius or some such thing. And again, so you can go ahead and create as many of these beasts as you like. And we'll just save that and exit. And I'm going to try compiling that just to see if I've got my syntax correct for those declarations. I'm not actually doing anything with the variable yet. And I'm going to turn on those warnings. And the warnings are probably going to tell me that I've declared these variables, but I'm not using them. We'll fix that later. Yeah, so it's telling me that I've created these 2 variables, age and temperature, that I'm not actually using. So as soon as we start putting values in them and start doing things with those values, those warnings will go away. But let's get back to our discussion, and then we'll see where we get to. So we've created these variables. We want to store values in them, and so there's this assignment operator, the equals sign, that basically says, here's a value I want to put in a variable. So you give the variable name, the assignment operator, the equals, and then the value you want to store in the variable. And again, a semicolon at the end. Those values can either be, a number of an appropriate type, or a character for character variables, or they can be expressions, right? Typical math expressions where you can use addition and subtraction, and multiplication and division and bracketing, and make as complex an expression as you like and store some value in a variable. And the things in there can be numbers, or they can be other variables, in which case it'll use the current value that's stored in that variable. And we can get this essentially work out a value and store it in a particular variable. So the way the compiler, or the way it runs during execution, is when it sees something like this, it looks at that expression, figures out what that evaluates to, and once it knows that number, then it copies it into that variable, overwriting whatever used to be in there. So we can do this as often as we like, and it just goes through our program from beginning to end, line by line, and whenever it sees an expression, it uses whatever the current values of those variables happen to be. And actually, just as an aside, you can actually do one of these assignments directly at the place where you first declare a variable. So you can do your int variable name and then assign it a value right off the start. Say, as soon as it begins, put a 5 in there, or put a 0 in there, or whatever your number of choice happens to be. So again, let's play with that just a little bit here. So let's edit our file. So this time, let's throw in, I don't know, let's say we'll start age off at 99. Let's start our temperature. Let's store a value of, I don't know, 12.4 in our temperature. And again, it's just whatever value we want assigned to whichever location we want to store it in. And you can do this kind of thing as often as you like. I can change, or I can add more variables. Let's add a couple more variables. Let's say X and Y and Z. So you can also take this kind of shortcut approach where if I've got a list of variables I want to declare that are all of the same data type, then I can just separate them by commas and say, okay, I can create an x and y and a z, and they'll all be integers. So again, you can go through and say, okay, well, let's set a value of 3 in x. Let's make y equal to age plus x. Let's make z equal to y minus x. Let's do it this way. Minus x plus age, I don't know why. But again, just making up expressions here. And in each case, it's going to go through and say, okay, well, I'll store a value of 3 in x. I'll use the current value of age and the current value of x, add them together, and store that in y. I'll use the current value of y, the current value of x, the current value of age, figure out what this evaluates to, and store the result in z. Right? So you can just go through and proceed as happily as you like, as long as you like. So let's give that a try and see if I've introduced any syntax errors. So we'll save and exit and compile. So this time, those warnings are letting me know that I've put a value in temperature, but I don't seem to be using that for anything, right? And which is absolutely right. If we look back at our code, we put a value in temperature, but we're not using this variable for anything. So the compiler is just saying, if you're not using this variable, do you really need it? And similarly with z, we put a value in there, but then we never did anything with it. And so the compiler's just kind of asking, are you sure you really want to be doing that? And if you're computing a value, don't you want to do something with it? So again, the compiler is attempting to be helpful here. Sometimes it's just annoying, but it's attempting to be helpful. So we can quite happily proceed as long as we want with this. We do, generally speaking, like to be able to display the values that we've come up with. Right? A program's not much use if it comes up with some brilliant answer and then never tells you what it is. So I'm just going to give you a quick look at what a typical printf might look like to display the contents of a variable. And in our next sessions, we'll get into the mechanics of printing out variable values in a little more detail. So we used printfs before to display just plain text. We can embed a variable value inside the text. And the way it's done is to say, I don't know, let's have a little prompt here for the user and tell the user that we computed the value of z as, and what I'm going to do is put a little placeholder in here that says a value is going to go here. And the syntax for C++ is we use the % symbol to indicate that if some kind of input value is coming up here, and then a character that tells it what kind of data it's going to be. I want this to be integer data displayed in base 10, displayed in decimal format. So I'm going to use a %d here. And again, we'll get into the gory details fairly soon. We end our string, and then we throw in a comma and say, okay, here comes the value that I want to put in that spot in the string. So I want to put whatever's in z in that spot in the string. Right? So this %d is for integer data. And then maybe let's do something similar with the temperature that we stored to show what it looks like for floats. The temp we were using is and a %f for floating points. And we'll throw in the contents of the temperature variable for that one. So we'll try a couple of printfs at the end here to go through and display the results we came up with. So again, let's try a save and an exit and try compiling and see if I threw any syntax errors in there. Let's see, what have we got? I did throw a syntax error in there. We're missing the double quote at the end of the second printf. So again, we can see that the compiler will let us know if it finds grammatical errors in there, syntax errors, and sure enough, it's right. I forgot to put my double quote at the end. Oops. at the end of my string. So let's try saving again, and exiting, and compiling. Yay, this time it actually worked. So now we can try running it and see if we get what we were expecting. So we computed the value of z as 0. Apparently I subtracted all the things that I added and wound up with nothing. So, so it gives us the value that we compute in z, and it computes the value that we stored in the temperature and displays both of those. So we can quite happily play with the variables and variable values as we go through this process. So in terms of basic computation, this is just kind of recapping what we just did. We can go through and store values in our variables. We can perform any amount of computation that we want, and it's always just figuring out what the stuff on the right-hand side evaluates to. Once it's got that answer, it puts it in the target variable. And it's always just using whatever the most recent value is for the variables in its expression. Now, one of the things that we haven't talked about yet is this idea of creating a variable and not assigning a value to it. So in this particular case, if I went through and created a variable x, and then let's say I just tried right away to assign x to y. Well, we haven't put any specific value in x. Depending on the compiler you're using, x might have some, ints might have some default starting value, but a lot of compilers just leave any old random value in there, just whatever happened to be sitting in memory wherever that variable happened to be located. And so it could be anything, which leads to really unpredictable program behavior. So it is quite common for people to come up with some default value that they assign to their variables when they first create them. But it is important to keep in mind that you have to make sure you initialize a variable before you try and use it. Otherwise, you really don't know what's going to happen. And quite often our compilers will give us a warning if they spot that we've created a variable and we haven't initialized it. So let's give a try with our previous example. So if I hadn't initialized age here, so let's just comment this out. And again, remember, if we throw those comment symbols in the 2 slashes, then it's basically telling the compiler, just ignore this. This is just kind of a scratch pad for the moment. So we are no longer assigning a value to age before we go through and try and use it. So let's see if the compiler actually gives us a warning about that. So we'll save, we'll exit, we'll try compiling, and sure enough, it goes through and tells us that age is used uninitialized in the function. All right. So we do want to remember to make sure we remember to initialize our variables. So basic data types that we talked about, we've really looked at int and float so far. There is another one called char for storing single characters. And the way you write a character value in a C++ program is to put it in single quotes. So if you wanted to store the single character x, lowercase x, in a character variable, in a char variable, you would just single quote x, single quote. If you wanted an uppercase, single quote uppercase x. If you wanted to store a question mark, if you wanted to store the digit 1, it would be a 1 in single quotes. So any one single character, and these pretty much correspond to, if you like, the keys on the keyboard. So any of the symbols on your keyboard, more or less, some of the special things like the deletes and the page ups and page downs and that sort of thing aren't supported, but the basic character set, you can put any one of them in a char variable. And we'll get more into the details of that as we get a little deeper in. Now, each of the variables we declare has a fixed amount of space allocated for it someplace in memory. It might just be a single byte of information for a char. It might be 4 bytes of information for an integer or for a float or something like that, but a certain fixed amount of space, a limited amount of space. And what that means is you can only hold so much data in that variable. How much space has been allocated for it for that particular system determines, like how much space an int is given, determines how big a value you can store. So it determines how big an integer value you can store in an int, or how big a floating point value you can store in a float. So there are limits on these things, and this varies to a certain degree depending on the system that you're working on. Each system will have a fixed size for ints, a fixed size for floats, a fixed size for other kinds of data type. On our system, just as it happens, the largest integer that you can hold, the largest int you can store, is that beastie there, which is probably 2 to the 15 minus 1, I'm guessing. Similarly, the largest float we can store is that. And again, it's based on the number of bits inside this storage space that are set aside to store the precision, and the number of bits that are stored or set aside to store the power of 10. So there is a very hard limit on what you can store in one of these things. And if you try and assign too big a value, then only part of it is going to fit inside the actual data storage location, and so it's only going to put part of it in the storage location, and you're not going to get the results that you're expecting. So there are very definite size limits, and so there are a variety of different flavors of integer data type. So there's a data type called short that's got less than 4 bytes, so it can only store tiny ints. There's int. There's also one called long that has twice as much storage allocated to it, so it can hold much larger integer values. Similarly, for floats, there's another one called double that has twice as much space as a float and can hold much larger real numbers and more precise real numbers. So these are things that we do have to be aware of. In terms of some of the other things that I wanted to bring up here is in our code, say we're going through and doing a whole bunch of computations that use the value of pi. We can either go through our code, and every place where we're going to do this, we can go through and actually type in whatever value we want to use, 3.1415 or some such thing, and just do that every place where we want to use pi in our computation. But if we later on decide I want a more precise or a less precise value for pi, then we have to go through our code and find all those locations and change them all correctly. And that makes maintainability a problem. What we would really like to be able to do is to turn around and say, well, can I declare a value to use for pi and just use the name pi throughout the rest of my program? So we could do that in a variable, but then the program could accidentally change the value of pi that we're using somewhere in there, right? Somebody actually accidentally stores or adds something to the variable pi, and we don't get the results we want because halfway through the program the value of pi changes. So what we can do is use what's called a constant. The declaration is going to look pretty similar to variables, but it's setting a value, it's fixing a value in a storage location and saying this value can't change. So the way it's done is by putting this const keyword in front of the thing we're declaring. So I want to declare a constant floating point number. I'm going to call it pi, and I'm going to assign a value to it. So for constants, the value has to be assigned right where you declare the variable. So you can say const float pi equals 3.1415, and throughout the rest of the program I just use the name pi whenever I want to use that value. So if tomorrow or next week or next year I decide I want a more accurate version of pi, I just change that one initialization statement and everything else is using my correct new value. So this is really important when it comes to code maintainability. And this is something that I'm going to emphasize quite a bit as we get into code standards fairly soon, where for producing quality code, I'm going to expect you to use constants for these values that you're storing throughout your program. All right. You'll often hear the term magic numbers used by programmers. And this is referring to places where people have some value hard-coded in their cases where they aren't using constants, where they're using something like 3.1415 directly in the source code, somewhere in the middle. So these are things that we're going to try and avoid. All right. A couple of other things that are going to crop up and be important are cases where we mix different data types. Ideally, if you've got an integer variable, you just put integer values in it. If you've got floating point variables, you just put floats in it. If you've got a character variable, you just put characters in it. But C++ does allow kind of a certain amount of crossover between specific data types. Cases where the compiler can recognize how to translate one data type into another. So, for instance, if we have a floating point variable and we assign an integer value to it, so here I'm using a literal value 3, right, a magic number 3, I could suppose I had an integer variable y. I could say something like, x is assigned y. In this case, putting an integer into a float, the compiler will generally say, okay, I'll permit that, and I'll just treat the 3 as being a 3.0 and store that. So it's pretty intuitive. Going the other way, it can be a little tricky. Let's say we put a float into an integer variable. Now, obviously, integer variables are only going to wind up holding ints. So somehow the compiler has to decide how it's going to turn that 2.9 into an int. And the way it does it, it doesn't round, it just truncates. So it just takes the 2 and stores that in our int. Now, one of the things that you have to keep in mind, if you remember how big our floats could be much, much, much larger than the ints that we could store. The biggest float we could store is much larger than the biggest int we can store. So if we try and put a large value in a float and then put that into an integer, again, we're going to run into this problem where the value won't fit, and it's only going to put part of the value into the variable, and you're not going to get the results that you expect. It's called overflow, and it's one of those cases where you have to be wary of it. And again, quite often, if we've got our warnings turned on, then the compiler will give us a warning if it spots places where we assign a float to an int, and it's going to say, yeah, there's a possible loss of data taking place here because you're trying to put something potentially big into something that's small. I believe the terminology you'll see in your error messages is something along the lines of a narrowing conversion. You're trying to put something big into something too narrow for it, if you like. So just heads up on things to watch out for. Similarly, you can wind up coming up with expressions. If I'm assigning the result of some expression to a variable, the expressions themselves can have a mix of data types in them. So you can do 3.0 or 3.5 plus 10, something along those lines, where you're adding a floating point number and an integer value. So what the compiler does is it goes through all the different expressions in your program, and if it sees something like 3 plus 10, it goes, oh, those are both integers. I'll just do regular old integer division. Most systems have different hardware to perform integer mathematics than to perform floating point mathematics. The integer mathematics is much simpler, the circuitry is faster and cheaper and whatnot. So if you're only operating, if you've got an expression that only works on integer values, it'll use the integer operations. But if there is an expression that has a mix of floating point stuff and integer stuff, then it's going to say, oh, well, I better use the floating point. So what it will do is compute 3.0 plus, and then 10 as if 10 was a float. So 10.0 if you like. So it's going to perform floating point addition and give you a floating point result. For the most part, the place where that's going to really matter is with division, because division in C++ is special for integers. If you perform integer division, it drops any fractions, right? So if I say something like 7 divided by 3, those are both integers, so it's going to do integer division. So it says, okay, 3 goes into 7 twice. There's a remainder of 1, but it just throws away the remainder. So the result of this is going to be 2. 7 divided by 3 as integers is 2. Similarly, 6 divided by 11, well, 11 doesn't go into 6, so it gives a result of 0. And again, it just throws away the remainder. So this is one thing to keep in mind. If you're dividing integers, keep in mind that it's throwing away the remainder. If you're using floating point, then it behaves as you would expect. So, 3.0 divided by 4, it's going to say, okay, well, that's a floating point result. It's going to give 0.75. If you're ever trying to get that remainder from integer division, so essentially, if you want to get the result plus the remainder, you have to do 2 steps, two divisions, if you like. One, say if I wanted to figure out what 7 divided by 3 was and what the remainder was, then I'd do 7 divided by 3 to get the 2, and I would also do a 7 modulo 3. So the percent operator is for modulo, so 7 modulo 3 gives the remainder. So 3 goes into 7 twice with a remainder of 1. 6 modulo 11, well, 11 goes into 6 0 times with a remainder of 6. So it gives back 6. So that is the one thing you'll probably need to watch out for in your math, is the integer division side of things. But again, hopefully we can get kind of a reasonable bit of computation going at this point. We can print out some basic values. We can create variables of different data types. We can store values in them. We can compute values. Again, we can compute values using things that we've computed previously. So you can come up with some reasonable computations now. And that's kind of where we want to get for our beginning basics of computation. All right, I will leave that there for now. Next time we'll get into a little bit more on output, displaying output on the screen, and input, reading input from the user. And once we've got that, then we can start creating some interesting programs.